Hello everyone, welcome to the Algorists. In this video, we will discuss Morris post-order traversal. I would highly recommend you to go through the videos and the contents we have in the algorists.com regarding Morris in-order traversal and Morris pre-order traversal. Going through those two chapters and those two videos first will really help you to understand this algorithm really well. So as I have already discussed in two other videos when we discussed about Morris in order and Morris pre-order traversal, that the main motivation behind the Morris traversals are to optimize the space complexity. So when we do a binary tree traversal using recursion or iterative way, it is an order of n algorithm. For iterative way, we explicitly use a stack, and and when we use recursion under the hood, it uses a call stack, and consequently that is also an big O of n space algorithm. And that is where Morris traversal comes into picture. It optimizes the order of n space complexity to constant space complexity. So at the heart of Morris post-order traversal algorithm is the concept of threaded binary tree. So to give you a very brief idea of what threaded binary tree um, is that in threaded binary tree we use the null pointers to do something really meaningful. Like here in this algorithm, we will see that we are using the right child of a predecessor of a node, and the right child will be a null pointer, and we will use that pointer to point to a node. And here the like for any node we will use the right child, which will be null, to point to the node. So the right child of the predecessor will point to the successor node. So the concept of using the null pointer of a node in a tree, in a binary tree, to do something meaningful, to do some optimization, comes from the concept of threaded binary tree. So let's see how we can optimize the space complexity of post-order traversal by doing the traversal according to Morris post-order traversal. So I will take two very simple binary tree. Yeah, so we know how post-order traversal works. So I'm assuming that, like, that you already know. If you don't know the basics about the post-order traversal, then I will post some links in the description of this video, which will have the link to the content where you can get all the information about how post order traversal works and how you can implement them recursively and iteratively. So I will quickly show you. um, you can go to the algorithms, and you can go to the uh, algorithms and data structure table of contents, and from there you'll have to come to the binary tree, binary search tree, and searching. And from there there, like, here is the content for iterative approach for pre-order, in-order, and post-order traversal. And I really encourage you to go through this chapter, because it really gives you some insightful information. And there is another chapter for recursive algorithm, and you can go over this like chapter to know how to implement the traversals recursively. So in post order, we know that we um, process the left subtree first, then we process the right subtree, and at the end we visit and process the root node. So for this tree, we will first we visit and process the left subtree. Since it does not have left subtree, we will visit and process the right subtree. So we come to the node with value 20, and then from there we do the same thing. We go to the left first and visit and process the nodes in the left subtree, and then to the right. But since both the left and right um, pointers are null, we visit and process this node by process here I mean just printing the value, and then we backtrack um, to the successor node, which is the node with value 10. And since we are like already processed the left and right subtree, we now process the root, and we print 10. So this is a very um, like very simple like binary tree, but it has a property that it does not have the left subtree, and we will need this one like while designing the algorithm, which we will see shortly in few minutes. That this is like we'll have to handle this case, that when like what do we do when we don't have the left subtree. And now comes uh, a binary tree which has both left and right subtree of the root. So so here how it will work. So I generally denote post order traversal as LRV, which means you visit the left subtree first, followed by right subtree, and then you visit the current node. So it will be the same for all. So let's see, we are at the root, we go to the left child, then we go to the left child of the current node. Now the current node is the node with value 4. um, we go to its left child, and we see that it does not have a left child, it is null. We check its right child pointer, that is also null, so we visit this node, so we print 4. Then we backtrack to its parent, and we visit the right child of the parent, which is 6. We visit like we check the left child pointer, we see it is null. We then check the right child pointer, and we see that it points to the node with value 7. It does not have any children, so we visit it and we print 7. We backtrack to 6, like it has no left child, its right child is already visited. We visit this node and print 6. Then we backtrack to node with 5, we visit it. Now we are back to its parent, which is the node with value 10. We visit the right child of it, which is node with value 20. We visit the left child of it, 11. It has no left and right children, so we visit it. Then we are back to its parent, which is the node with value 20. We visit its right child, but we see it has none, so we visit it. Now we are back to the root. Since its both left and right children are fully processed, we first process the entire left subtree in the post order manner, and then we traversed its right subtree in the post order manner, and now, so since both its left and right subtrees are visited and processed, we will now visit the root, which is 10. So just to give you a brief idea that how it would look like if we implement this iteratively using a stack, um, we would start with the root, which is value 10. We would push that in the stack, and we would push its right child first, followed by the left child, the value of the left child. um, then we would look at what is on top of the stack, and then we would push its, and we would see its node with value 5. We push its the value of its right child first, followed by 4. So now 4 is on top of the stack, and we see that it has no left or right child, so we pop 4 and we print it. We see there on top of the stack we now have 6, um, and it has no left child, but it has a right child, which is value 7, so we push 7 in the stack. Now we see that 7 is on top of the stack, but it has no children, so we pop 7 and we print it. Now 6 is on top of the stack, and we see that both its left and right children are processed, so we pop 6 and we print it. Now 5 is on top of the stack, and both of its left and right subtrees are processed. We pop 5 from the stack and we print it. Now we have 20 on top of the stack, and it has 11 as it has no right child, so we push nothing for the right child since it is null, but we push 11 as its left child. 11, so now 11 is on top of the stack. 11 has no children, we pop 11 and we print it. Now 20 is on top of the stack. Both of its left and right subtrees are processed, so we pop 20, print it. And now 10 is on top of the stack. We pop it and we print it, and we do this operation till the time the stack is not empty. So since stack is empty now, our traversal ends here. So this shows you that why we have big O of n space complexity for the traditional way of doing post order binary tree traversal, and this is where Mori's post order traversal will come into play, and it will optimize the space complexity from order of n to constant space, which is a massive improvement. So let's see how the Mori's post order traversal works. um, let's do step by step. um, at any point of time, the node on which we are at, let's say we say that we call that node a current node. So let's talk about the first small binary tree, and say we are at the root. So we know we first need to traverse the left subtree followed by the right subtree, but in this case we don't have a left subtree. So what do we do? We have nothing to do with the left subtree, so we just go to move on to its right child, and then we will see that how we come back to the root node to actually visit and process it. And we will see that for that we will have to do a trick, we will be taking something called dummy node, but we will talk about that later. So if the current So I'm just doing it step by step, so that we can easily convert our thoughts into a working code. um, so if current node has no left child, then just move on to the right child of the current node, and then later we will see that how we come back to the root to print its value. What is the second scenario we can have? The second scenario is obviously when um, the current node has a left subtree. So here we are dividing the whole process into two parts. um, so here we see that we need this stack because we don't know how to go to the successor node from the from any node, like how to go to its successor node, like how to go to say 11 from 5. We don't know that. So that's why that is where the stack is helping us to keep track of that. So this is where we use the concept of threaded binary tree. So how about when we are at the root, we have and if you have already watched the video and read the contents on Modi's in order traversal, this would look very familiar to you. How would we have a pointer here, a threaded pointer here, and so for 7 we have right child as null. So how about we modify the right child and we point that to the successor node. So here 10 is the in order successor for 7. So if you see, we are first processing the whole left subtree, and the rightmost node of the left subtree is 7, and from there if we come back to 10, and then from 10 we can go to its right subtree and process that, and then somehow come back to 10. And I'm saying somehow because that is how we come back. We will discuss, and that is through taking a dummy node, which we will discuss later. So whenever we are at any node, um, we will first check if the predecessor has already been computed for that or not. And when I say predecessor, it is the in order predecessor. So for 10, the in order predecessor is 7. We do that, and we move on to its left child, and then we do the same thing for the left child. We compute the in order predecessor for the current node, for the current node which is this node with value 5. And then if it has a left child, we move on to the left child, which is 4 here. So for 4 we see that there is no left child, so we move on to its right child, and we have already modified its right child to point to the successor node. So we go to 5, and now we go to its right child. So we go to 6, we see that it has left child as null. So we move on to its right child, and its left child is null. So we move on to its right child, and we see that this happens to be a predecessor node, and it has its right child pointing to the successor node, which is 10. So, as I mentioned before, this part will be divided into two parts. We search for the predecessor twice. Once, when for the current node we don't have the predecessor, so the whole objective in that part is to actually compute the predecessor. And in the second part, we again look for the predecessor, and this time we see that the predecessor has already been computed, and that is how we know that this is our second visit to that node, and we need to do a different set of operations than what we just did, like discussed, like than what we just did in the first time field like visit, like when we are actually computing the predecessor for the first time. So what we did like discussed till now was what we do in the first time visit, when the predecessor is not yet computed and we are computing the predecessor. Now we will see that we are in the node with value 10, and we will see that its predecessor is already computed, and we will see that what we will have to do for this part. So we see that um, this 7 is a predecessor of the node with value 10, and so we see that it has left a subtree, non-null left subtree. So we look for its predecessor, and we see that it already has a predecessor. So in the code we will see that how we figure that out, that the predecessor is already computed. But I can give you a brief idea here. So if we iterate, um, if we traverse this path, we will see that we are back to the same current node, because we already have the connection from the predecessor to the current node. So that is how we would know that the predecessor was already computed. Yeah. So what we do now is we traverse along this path till the predecessor, and we change all the right node, or all the right child pointers of the node in our path. So we are in the node with value 10, which is our current node. We go to its left, and we put the right child of the left child of the current node. So the current node is the node with value 10. Its left child is node with value 5, and we are going to modify the right child pointer of the node with 0.5. So that's why we need to keep the already existing right child of the node with value 5 in a temp, and we change the right child pointer to point to the current node. So we are the current node, we go to its left child, and then we change the right child pointer of the left node, and, and then we go to the node with value 6, and we do the same thing. We change the right child pointer and point it to its parent, like to the node of which it is a right child. So 6 is the right child of 5, so we point to the parent node using its right child pointers, and definitely we keep its previous right child to a temp, and when we come to the node with value 7, we modify its right child pointer and point to its parent. So you can see now the right child of 7 no longer points to the node with value 10. And if you have noticed, So till now we have processed, like we have printed only 4. So 4 was already printed. After that, if you look from here, 7 needs to be printed, followed by 6, followed by 5. So we are right now at node 7. So we came all the way from node 10, like node with value 10, to node with value 5, then 6, and then 7. So we are at the node with value 7. Yeah, its right child point to 6, its right child point to 5. And that is exactly how these three nodes needs to be printed. So we start from 7 and we go on printing along its right child till the we hit the current node. So don't forget that the root node is still our current node, and we are in the part where we have visited this node for the second time, and all these operations we are doing as part of the second visit when predecessor has already been computed and we are visiting for the second time. So we go on printing this node till that time we reach the current node, but we don't print the current node because remember, this is part of processing the left subtree. So after this we need to process the right subtree, and only then we can process the current node. So the left subtree of the current node has not yet been processed, so we cannot print 10. But first, so starting from 7, we print 7, go to its right child, which is 6. Then we go to its right child, which is 5. Then we go to its right child, and we see that we hit the current node. So we don't do anything there. So now we know that the whole left subtree is processed. So what we need to do is process the right subtree now. So what we do now is we move on to the left child of the current, I mean the right child of the current node. And here we follow the same process that we discussed till now. So here we see that 20 has left child, so we can compute its predecessor. So we see that, yeah, the node with value 11 is the predecessor. We change, we modify the right um, child pointer of node with value 11 and point it to the successor node, which is the current node 20. And then we move on to the left subtree, the left child with value 11. It has no left child, so we move on to the right child. So it brings back to the node with value 20. So now we see that it already has a predecessor. So this is the second visit. So we do the same thing as we did earlier. We go to the right, we go to the left child, and from there we traverse all the way to the predecessor, and we go on changing the right child pointer for each of the nodes. So for this scenario, the left child also happens to be the predecessor. So we change the right child pointer of the predecessor to the current node, and that is already done. So even though we are saying that we are changing, in this particular case it is not changing at all, but from here we will go to the next operation, which is printing the nodes till we reach the current node. But we don't print the current node, we print all other nodes in the path from the predecessor to the current node, following the right pointers from each node, and we print till we reach the current node, but we don't print the current node. And the reason for that is we just process the left subtree, and we still need to process the right subtree. So we started from the predecessor node, where we printed the predecessor node, and we are back to the current node, which is 20. So we are not printing this node's value as part of this operation. Okay, so you remember that I was talking about the dummy node that we will need, and we will discuss now that why we need that. So all the nodes are visited and printed except 20 and 10. In general, we need to print all the nodes in the path of the starting from the root node, and all the nodes which happen to be on the rightmost path of the right subtree. So I call them node of type root. So say if we have a tree like this, and then it has its own left subtree has its own left subtree, it has its own left subtree, and then its own left subtree. So if this is the root, and this is the right subtree, and this is the rightmost path. So all these nodes, I call them of type root, because and their characteristics is, for this particular scenario, they are on the leftmost path. Sorry, they are on the rightmost path in the right subtree, and each of them has um, subtrees of their own. So that's why I call them um, like nodes of type root. So we need so now we are stuck where all the nodes are printed except for these nodes of type root, like for this particular scenario. So how do we print this path? So for this example we have here, the path is really small. We have only two nodes on this path, and how do we print these two nodes in the correct order? This problem can be solved by taking a dummy node. So see here, like when we were printing 7, 6, 5, and they also happen to be nodes of type root, and they were on the right side of the node with value 5. So and this is very important. Please pay attention here. So 6 and 7 is on the right side of 5, and they are of type root. They are on the rightmost path of the right subtree of the node with value 5. So we printed this whole path when we were processing the root node, uh, the node with value 10. When we visited the root for the second time, when the predecessor was already computed, like at that time we printed these nodes as part of the processing we did when we visited the parent of 5. So node 10 is the parent of 5. So when we visited the parent of 5 for the second time, so we would have to do the same thing to print the rightmost path of the right subtree of the root, and for that we need a dummy node. So how about we take an additional node here, and you can put any value here, like any value that you know that will not be in the tree. You can take, say, max int, and you make the given root as the left child of the dummy node. So see how it is very similar to what we did before. We printed 7, 6, 5 in the correct post order, in the correct order, that should be in the post order. When we visited the parent of 5, and 5 was the left subtree of its parent. We are doing the same thing. We are making the root the left subtree, the left child of the dummy node. So when we write the code, we will actually create this dummy node at the very beginning, after of course doing the null check of the given node and all. And we will make the root the left child of this dummy node, and we will start the whole processing from dummy node. So our current will actually start from dummy node. Um, and since 10 is the given node with value 10 is the left subtree of the dummy node, it will compute the predecessor. In this case, the predecessor will be 20, because of course 20 is the rightmost node of its left subtree, because we are taking the in order predecessor here, and then we are tweaking the following steps to make it post order. Um, so we will already have the right child pointer of the node with value 20 pointing to the dummy node, and this is the threaded node concept, the threaded pointer concept from threaded binary tree here. And so when we are at 20, then if you really remember where we got stuck, and we were discussing, we drew this diagram here. So we start at 20 because there was no way to print 20 and 10. So if we started with the dummy node, when we came to 20, um, after we processed its left subtree, and when we are back to the current node, to 20, from there we would go to its right subtree. So after visiting, not really visiting, after processing the left subtree of 20, we go to its right child, and since 20 is predecessor of the dummy node, the right child pointer will point to the dummy node. So we reach the dummy node there, and we will see that this is our second visit, because the predecessor pointer was already there, because that will be computed at the very beginning. So this is our second visit. So we see that we have a left child. So we go to the left child, and from there we go all the way to the predecessor, and we go on changing the right child pointer. So as we have already done before, the right child pointer of 10 will now point to the dummy node, and the right child pointer of 20 will now point to the given node, the node with value 10. And then, as we have done before, starting from the predecessor, even though we have changed the right node um, pointer, but whichever node was the predecessor, we start from there. So for in this case, 20 was the predecessor, and we go on printing till the time we reach the current node. So we are at the dummy node, we reach there, but we don't print that node, and this is exactly what we have done before. So we are at 20 now. We print to 20, we go to its right child, which is 10. We print 10. We go to its right child, and we are back to the current node. So now the whole left subtree of the current node, which is the dummy node, is processed. So we go to its right subtree, and right subtree of the dummy node is null. So we make the writes child the current node, we terminate the processing when the current node becomes null. So that is uh, like when we end the process and we know that the post order traversal has been done. Now I will briefly discuss the algorithm, how we actually implement it, but you would find the working code for Morris post order traversal in this link. It is in our website, thealgorists.com, and if you go to this link, you should be able to see the content here. So we already saw we take a dummy node, we make the given root the left child of the dummy node, and then we make dummy node the current node, and we process till the time current is not null. So we first check if current has a left subtree, and if it does not have a left subtree, then we do not like, nothing other than just moving on to its right child. Else, if we have left subtree, then we compute the predecessor. And the chapter on Morris post-order traversal in our website, thealgorists.com, has the full working code on how we would do each step here, how we would compute the predecessor, how we would know that if it is first visit. So if it is first visit, then just modify the right child pointer of the predecessor. So this is one, and second, we just move on to its left child. But if it is second visit, then as we saw, we need to do a like bunch of things here. We need to change a bunch of right child pointers. So modify right pointer for nodes in the path from current left to predecessor. And we have shown that how we would do this modification and what exactly actually needs to be done here. And after we have done this, we actually start. So this is one and this is two. We start from predecessor all the way up to current dot left and print their value. So after you have done this, you will have to move on. So this, um, if we have come till here, this means that the left subtree of the current node is processed. So now just move on to the right subtree. So and will this while loop will go on till the time we have the current node not equal to null. So this explains the whole algorithm. And in the chapter in our website, the algorithms.com, we have also shown how we can actually really recover the right pointer um, modification that we have done for the predecessor node. So please visit our website and read the content we have there on Morris Postorder Traversal to know more about the algorithm and to know about the recovery process of the modification of the right uh, child pointers of the predecessors. And you can access the contents in our website from this link. So it was great talking to you regarding Morris post-order traversal, um, and we will come back with more interesting algorithms like this. So thank you, and I will see you in our next video.